We're going to move from some more fundamental processes in global tectonics and talk about passive margins and ocean spreading. The topics that we'll cover will include the progression from rifting to passive margin and ocean spreading, volcanic versus non-volcanic rifted margins, and the differences between fast, slow, and ultra-slow ridges. These diagrams show the progression from rifting, where we have non-marine flood basalts and intrusions into crust, and terrestrial sediments filling basins that are formed in the area that's beginning to rift. Then we move on to the rift-drift transition, where we begin seafloor spreading and have a shallow sea forming and evaporate deposits. Then we move on to the drift process after 5 to maybe 100 million years, where we've got the formation of a passive margin and marine carbonates and terrestrial carbonates covering the rift-drift sediments. So in these areas. Passive continental margins join continental and oceanic lithospheres across a broad and often deeply buried transitional lithosphere. And so in this diagram, we see a broad, shallow shelf. The shelf break at about 200 meters, the continental slope, and then finally the continental rise as we progress out from the continental margin. The shelf is underlain by thick sediments, and this transitional crust is a stretched and faulted continental crust. Now we have two end members of this transitional crust. We have volcanic rifted margins, where the transitional crust is underlain by magmas, and it's made up of magmatic intrusions, versus a non-volcanic rifted margin or a rifted passive margin, where the transitional crust is comprised of stretched crust and magma plays a much more minor role. If we just look at some cartoons of the differences between the volcanic and the non-volcanic rifted margins, you'll see in the volcanic rifted margin that there is significant amount of intruded melt, and that we have some lavas forming where those magmas have been extruded, and that there are seaward dipping reflectors. If we look at a non-volcanic rifted margin, you don't see the same kind of underplating of melts. There is exhumed serpentinized mantle, and there is a very extended magma pore continental margin. Now, of course, these are end members and theoretical end members, and probably each passive margin, rifted margin, is somewhere in between these two end members. Okay, continuing to look at volcanic versus non-volcanic margins. Now, originally, these rifted margins were thought all to be non-volcanic, and then volcanic rifted margins were recognized as a special case, and now it's really flipped, and volcanic rifted margins seem to be more common than the non-volcanic rifted margins. So how we define these, volcanic passive margins, rifted margins, have high P wave velocities, so higher than 7 kilometers per second in that transitional crust. And the volcanic passive margins have the seaward dipping reflectors in the transitional crust. Whereas non-volcanic rifted margins have more modest P wave velocities of about 6 kilometers per second in the transitional crust, and they have continentward dipping reflectors in that transitional crust. And this diagram is showing you the volcanic rifted margins around Africa, India, the east coast of South America, North America, around Greenland, and up in the Caledonites. And you see other places where we have non-volcanic rifted margins that are more rare. Now, the origin of these seaward dipping reflectors are from overlapping lava flows in the volcanic rifted margins. And so we have a progression over time where we have lavas deposited on top of one another, and ultimately you've got the sequence of seaward dipping reflectors from those lava flows. And this example is from just east of Greenland and west of Norway, where the seismic work shows these seaward dipping reflectors from the volcanism at that margin. Now, the origin of the landward dipping reflectors in non-volcanic rifted margins are from rotated sedimentary packages and half grabens. So we have the normal faulting that is helping to extend the crust, and those half grabens are filled with sediments that are being deposited in the basin that results. Now, these non-volcanic rifted margins include hyperextended margins where we have mantle exhumation and a dramatic asymmetry of the upper plate versus the lower plate margins. So the upper plate being the extended continental crust and the lower plate being the exhumed mantle and oceanic crust. The origin of this asymmetry is really the difference between, if you look at the top, this asymmetric, more simple shear sort of environment where we have a low angle normal fault or a detachment underplating those higher angle faults in the upper plate that then migrate down into the lower plate along these half grabens, versus a more pure shear kind of model where we have two or symmetrical detachments underlying the extended crust and these half grabens. So this is really an inheritance from the rift stage in those margins. Now, if we look at more at the upper plate versus lower plate margins, we see that changes from the upper plate to the lower plate happen across transfer faults or transform faults that underlie the detachments and change dip and the sense of rotation of the overlying tilt blocks. So here, look at the cross-sectional view of that to see the detachment underlying those tilt blocks. And then if extension continues until an ocean basin forms, the transfer faults mark changes from the upper to the lower plate margins. And this is something that's been interpreted for the U.S. African margins as upper and lower plate. So you can see this asymmetry in a detachment separating those two plates and the tilt blocks in the overlying rocks. So possibly crustal thinning by these conjugate concave downward faults with large amounts of extension that are forming very thin crust and exhume the mid crust and finally mantle material with this very depth dependent stretching. And so if you start with, in the pre-rift stage, this high angle normal faulting that leads to these tilt blocks, and then finally the formation of these low angle detachments, and ultimately exhumation of upper mantle rocks. The transitional crust is capped by these sub-horizontal detachments for distances over 100 kilometers. But this is something that hasn't been imaged on seismic data yet. So the sequential high angle faulting with a progressive fault block rotation is in an evolving thermal structure, and the early faulting has uniform stretching of the brittle and ductile crust. Extension is slow, so the lower crust becomes cool and brittle as the late faults cut down through to the mantle. And so the strength profile of the lithosphere changes from a strong upper crust, a weak lower crust, and a strong upper mantle to a strong upper mantle, a strong crust and upper mantle together. Now, if you look on the right, we see the progressive fault block rotation and the crustal thinning. So first, the high angle normal faults, eventually a detachment, and as those high angle normal faults rotate to lower angle, that continues to progress until we those faults reach down to the mantle as the crust is thinned. And then we develop those lowering and normal faults that are actually exhuming upper mantle. So there's no active low angle normal fault and no depth dependent stretching. This last stage where we have this exhumed, buoyant, serpentinized mantle, we're seeing a progressive embrittlement of the lower crust and mantle serpentinization once the crust is brittle and once the faults have cut down into the mantle. That process requires magma inhibition during the mantle exhumation. So cold mantle temperatures, colder than normal, so 1200, 1300 degrees Celsius. Mantle depletion, so in the basaltic constituents, so it's a non-fertile mantle that delays the melting and reduces the melt production. And or we have ultra slow extension, so less than 6 millimeters per year with half rate extension, allows the mantle serpentinization at the moho and simultaneously with or immediately prior to any decompression melting that's happening at depth. So these volcanic and non-volcanic rifted margins are fundamentally different. There are two examples here of a volcanic rifted margin between Greenland and northwestern Europe, where there have been imaged these melts that have been intruded into the transitional crust, these seaward dipping reflectors, versus this hyperextended magma pore margin like Iberia and Newfoundland, here and there, where we've got this hyperextended magma pore margin, the exhumed serpentinized mantle, and the sediments filling these half-graben basins that are formed. Now here's an example from the Woodlark Basin in Papua New Guinea, or near Papua New Guinea. That is a young rifting center and very young or proto-continental crust that's forming. And it gives us an example of how rifting proceeds to spreading. So this is an active continental rifting that's ongoing and evolving to oceanic spreading within that proto-continental crust. So this blue area is the region that I'll show you in the next diagrams. This is surrounded by several subduction zones beneath the Solomon Islands, beneath the Papua New Guinea and New Britain. So it's a complex tectonic setting where this is all ongoing, but we have evidence of how these processes evolve from initial rifting to ocean spreading. This is the Woodlark Basin. Again, that's an area in blue. And we still see the subduction zone there. another subduction here, the transform fault that separates the two subduction zones, and then the spreading centers that are marked here in gray that cut down the middle of this woodlark basin. And what we see are this time progression from 4 million years to 1 million year. The breakup is proceeding by successive phases of rifting localization at 4 million years, continuing on to spreading center nucleation at 3 million years, the propagation of the spreading center and the stalling at 2 million years, and then a jump across an offset to the next side of localized rifting at 1 million year. So these accommodation zones focus spreading nucleation to the centers of the late-stage rift basins where normal faulting and crustal thinning are maximized. And then early propagation of nucleated spreading segments and the subsequent transform developments across the non-transform spreading centers typically removes any correlation between the segmentation of the rift margins and the spreading centers themselves. If we look at the rifting localization stage, we see that numerous rifts are destined to fail. They are beginning by having an area of distributed faulting, and we can compare this also to examples in the North Sea in the East Shetland Basin. We have a low slip rate with many inward and outward facing faults. Then in the second stage, we have strain localizing onto a large inward dipping fault arrays. We have half grabens forming with an increasing slip rate. And finally, in the third stage, strain migrates toward the rift axis. And the rift axis is clearly defined with a high slip rate, and then lower slip rates persist on the margins. In the spreading center nucleation stage, we have late stage rifting that's focused extension into rift basins, and that's delimited by a long strike accommodation zones. Volcanoes are locally extruding magmas. Upwelling asymmetry feeds the magmas into the thinning continental lithosphere. And the magmatism nucleation nucleated a spreading center that propagated quickly at 500 millimeters a year, or 50 centimeters a year, to both ends of the basin, and that produced a subparallel rift and seafloor fabrics. So this fabric that we're seeing that's subparallel to that. In the last stages where we have spreading center propagation, the intermittent stalling, and jumps across to an offset to the next side of localized rifting, we see the segments are propagating to the west into lithosphere that has its main rifting locus that's further south. And it forms a continent-ocean boundary that's discordant to the oceanic isochrones and continental structures. The fourth segment nucleates on the main rifting locus that's further south, and it's offset by a transform fault from segment 3 and rapidly progresses westward. We can see these structures imaged by seismic data where we see these rift basins forming and the normal faults that are thinning the crust. We can also see part of this process where we have magma intrusion through these areas where the seismic waves aren't giving us any reflectors. So you see these high angle normal faults that are interpreted on the lower diagram. And this area here is interpreted as a magmatic intrusion and then dikes feeding the rift. This is a complicated figure, but we can walk through it together. Let's look at the lower part of the figure first, and we're looking at the western extent of this rift system to the east. And the green area of this is showing us that in the west, the width of the continent, the continental crust, is large, and that that thins as we move east. And the red part of this diagram is showing us the oceanic lithosphere width. And so that's widest in the east as well, and narrowing to the left. So we're seeing, as this rift system grows, we're seeing the amount of continental crust shrink as the rift is opening and the oceanic spreading center is actually opening and spreading apart. And we're seeing the width of the spreading center grow on the eastern side. And basically this area in the middle is where we actually see oceanic spreading. Now, the continental crust that had spread or stretched older than about 6 million years, that's now subducted. And based on this diagram, we see that the onset of spreading at about 3.6 million years, and that spreading propagates westward at a rate of 140 millimeters per year. The upper diagram is showing us continental extension in kilometers, and we're seeing this blue line show us that before spreading started, there was extension taking place, and that breakup of the continent began at the point when extension had reached 200 plus or minus 40 kilometers. And then we see several places along the system where we have nucleation of a new spreading center, and many places where there's propagation of the spreading center at the P's, and that there are places along the system where we also see stalling. So it's a stop and start kind of process. It's not a smooth transition from continental crust to oceanic spreading center. And I can put this next to the topographic map that we looked at before. When you looked at that, was the continental crust on the west that was still wide, and that the oceanic spreading centers are widening from west to east. Now we can consider the different kinds of spreading centers globally. And spreading centers range from fast to slow and even ultra slow. You can see that the Mid-Atlantic Ridge is considered a slow spreading center. Beyond that, in yellow, even ultra slow. Others, like the East Pacific Rise, are fast spreading centers. There are about 40,000 kilometers of ridges globally, and around 20 cubic kilometers of new oceanic crust is created each year by this mid-ocean ridge system. And then looking at the speed of these ridges from ultra slow down here at around 10 millimeters a year to fast at between 80 and 90 millimeters per year. We can compare that to the ridge length up to 5,000 kilometers. And what we see are that the slow and ultra slow ridges form the longest ridge segments, and the fastest make up the shortest spreading centers. Now, it's not only the supply of magma that is driving the speed of these ridges, but there is another first order control on spreading rate, and that is the percent of the plate margin that is convergent. So, are these spreading ridges surrounded by subduction zones? Fast spreading ridges are surrounded by subduction zones, like the East Pacific Rise. And the amount of the percentage of the circumference of the plate that's connected to one of these subducting slabs can be upwards of 30% of the plate. And in slow spreading ridges, very little of the surrounding plate is actually surrounded by subduction zones, like the Mid-Atlantic Ridge. This gets at the idea of the issue of slab pull versus ridge push driving the systems, and that is it the buoyant magma pushing up beneath these spreading centers that is driving plate motions, or is it the pull of a downgoing subducting plate that is being metamorphosed, becoming more dense, and pulling the plate behind it? And some would argue that ridge push is important, others argue slab pull, but the slab pull must be an important driving force. We'll continue the comparison and look at topography along the ridge axis. And for a fast ridge system like the East Pacific Rise, what we see is relatively low relief. This is 15 times vertical exaggeration, and so it looks like there is a lot of topography. But relatively low relief, that there is an axial rise in the center of the ridge system. Compare that to a slow ridge system like the Mid-Atlantic Ridge. And what we see is the opposite, extreme relief. So this is 5 times vertical exaggeration. We see an axial valley, and we also see long-lived transform faults above this line. And in between, of course, is the intermediate tight ridge. We see relatively high relief. There is an axial valley, and an example of this would be the Southeast Indian Ridge. So we considered the length of the ridges and the speed, what the topography or the relief is like across the ridges. And let's look at segmentation and discontinuities in the ridge systems as they relate to the supply of melt. And what we see are in fast ridge systems, there is little segmentation. And we compare as we blow up different parts of these ridge, but there's relatively little ridge segmentation. Whereas in a slow ridge system, we see that there are offsets, discontinuities all along. And this relates to the supply of melt. And so in a fast ridge system, we have a lot of melt available. There's a melt reservoir along the axis of the ridge. And the supply of that melt is leading to these continuous ridges, whereas a lack of melt in a slow ridge system means that the upper crust is behaving more rigidly, and we end up with discontinuities and segmentation along the length of a ridge system. Now, the spreading rates can define the magmatic supply, i.e., if there's a lot of magma available, we get faster rates. Presumably, the morphology also relates to the supply of magma. And so again, in a fast ridge system like the East Pacific Rise, we see low relief compared to in a slow ridge system like the Mid-Atlantic Ridge, where we see more extreme relief. And another thing to point out, these are axial profiles on the right, so looking along the axis. And just notice that along the length of a fast ridge system, we see gaps in the magmatic supply. Slow spreading ridges can have an inflated ridge morphology if they're near a plume, and here we're considering Iceland, where there's a plume. Well, it's a topic of debate, but there's likely a mantle plume beneath Iceland, and it's also along one of these mid-ocean ridge systems. This Reykjanes ridge sits much higher up in the oceanic crust because of the heat from that adjacent mantle plume. We can look at what's driving the extension, and in a fast ridge system, we see zones of low velocity that correspond to magma, and those also correspond to shallow water depths, a broad ridge, so a wide ridge area, this low velocity zone, melt lenses that are ubiquitous, and thinner crust above those magmatic systems. In a slow or ultra slow system, there is very poor magma supply. We see a deep rift valley floor, a wide valley floor, a narrow low velocity zone corresponding to this magma. The melt lenses are rare, and there's a really variable crustal thickness, in part because of the differences in relief along the ridge axis. Now, an example of the East Pacific Rise, we can image magma chambers and these low velocity zones, these reflectors that look like the bold dark lines, are the tops of magma chambers, and can see that there is a continuous supply of melt beneath a ridge system along its axis. And we can look at seismic velocities as well and see zones of low velocity here in darker orange that correspond to slower S-wave speeds, and see that there is a supply to these ridge systems from inflow from adjacent parts of the mantle. And so the supply of melt isn't coming necessarily from the area of the mantle immediately beneath the ridge, but this lateral inflow from other parts of the mantle.